All right, we're ready to start section 1.9, and this is matrix linear transformations. And I just call your attention on page 71, there, that bottom of that first paragraph. It says, the key to finding A is to observe T is completely determined by what it does to the columns of an n-by-n identity matrix I. So it's just, A is just a transposition of the identity matrix. And if you look at theorem 10, then it's telling you that the transformation from a space Rn to Rm is a linear transformation. Then there exists a unique matrix A such that the transformation of X is AX. In fact, it says A is an m by n matrix whose jth column is a vector T Ej, and that Ej is the jth column of the identity matrix. So the transformation is on the identity matrix, and that the Ej is a column from that matrix. It's telling you a couple more things that are probably important as you read through. Is underneath the proof of that theorem 10, it says the matrix A in 3 is called the standard matrix for the linear transformation. So just it is a transformation on the identities. Now example 3, there's an important matrix there, A, when it's a rotation, positive angle rotation about the origin, and that rotation is always at cosine beta, sine beta, minus sine beta, cosine beta. So that is a when you do rotations, and then it's just whatever the trig function is for that. And then once again in that geometric linear transformation, that paragraph, the second sentence down, it's once again reminding you that transformations are linear. They are determined completely by what they do to the column matrix of the identity matrix. If you look at the next page, 74, you can see that those transformations are all working on the identity matrix. When you transform something around the x-axis, essentially if you x2 and x1, if you think about it back in your college algebra days, that it's y and x1, and if you transform it around the x-axis, the y becomes a negative y, right? You do minus f of x, and notice that transformation is 1, 0, 0, minus 1. So that y value, 0, minus 1, that identity where it's working on your y becomes negative, and that's the rotation. So it's a transformation of 0, 1 to 0, minus 1. And then likewise, when you go around the y, here it's called x2 axis, but when you go around the y-axis back in your algebra days, it was f of minus in the bracket. If you remember you recall what I'm saying? If you have a function like this, when you did that, you rotated around the x-axis, right? That was a rotation around the x. Yeah. Wasn't what I wanted to get. But anyway, this was a rotation when if you had some function, and the typical one was like this, if you rotated that, it rotated it this way, right? And that's what they're talking about there in that first one, when it says 0, 1, 1, 0, 0, minus 1. That's that rotation around the horizontal. And then the rotation around the vertical was when you did like this. And then what happened is this thing rotated into this position. And notice that they've taken the identity and they've taken the x, 1, 0, and made it minus x. So it's the rotations are what they're doing to the identity element. When you're rotating it around that diagonal line, then you can see that the rotation is they're taking the identity 1, 0 and making it into 0, 1, and then the 0, 1 into 1, 0. So you can see how they're taking all of those E1, E2, and E3 and transforming them into different values for whatever transformation they're asked to do. And on the page 75, there's a stretch and shrink horizontally, and then a stretch and shrink vertically. And you can see that it's the Y value when they do vertical. And then the shears. So now on page 76, it's talking to you about the mapping T from the space Rn to Rm is said to be onto if Rm onto Rm if each B in Rm is an image of at least one X in Rn. If you go to the next page on 77, you see that those two mappings, both of them are onto, because each image in that Rm is from an image in Rn. But if you look at the definition for mapping on one-to-one, then only the right-hand one is one-to-one. It has to be one element in the domain, one element in the range. And that should be familiar to us from the algebra days. And when it's one-to-one, remember that then you can do inverse functions, right? You can't do inverse functions if it's not one-to-one. So that's that mapping. Okay. So the theorem 11 says when you're doing a transformation from Rn to Rm, to be a linear transformation, then T is one-to-one if and only if the equation T of x equals 0 has only the trivial solution. So that information, along with this theorem 12, is going to allow us to work our problems. There the transformation says A be a standard matrix for the transformation, and T maps Rn to Rm if and only if the columns of A span Rn. And the T is a one-to-one if and only if the columns of A are linearly independent. So those things allow us to be able to identify the different matrices that we have to have for transformations. So let's look at the problem set 1 through 10. It says assume that T is a linear transformation. Find the standard matrix T, and it says T transforms 3 to 2, and then they're saying that T is 1, 3, and so on, where E1, E2, and 3 are columns of the 3 by 3 identity matrix. So they want us to calculate so they're giving us so they're taking those different identity elements from the identity matrix and then transforming them into these. So that this transformation matrix is just these transformations. So each one of your columns are going to be so you make that matrix, it's just 1, 3, and then the next one was 4 minus 7, and then 5, 4.
Minus 5.
Is that minus 5? So that's your A matrix for the transformation from the R3 to R4. Now 4, it's saying it rotates it clockwise pi over 4. So for that particular one, would use, if it's clockwise pi over 4, then it's counterclockwise. It's 7 pi over 4, right? So you use that matrix. It's counterclockwise. See what you're doing is that rotation is back there where it says in example 3 on page 73, it says a counterclockwise rotation for a positive angle, and it's this matrix. Counterclockwise. Because if you go clockwise pi over 4, there's 2 pi in one complete rotation, right? So that'd be 8 pi over 4, and then you subtract pi over 4, so that'd be 7 pi over 4, right? Those two are equivalent. It's 8 pi over 4 minus pi over 4. It's going to give you that rotation. And then the matrix is that cosine of n sine clockwise rotation of the angle, cosine of the angle. So what you're going to do is you're going to do A of cosine of 7 pi over 4 sine of 7 pi over 4 minus sine of 7 pi over 4 and then cosine 7 pi over 4. And the cosine of 7 pi over 4 is 1 over the square root of 2, right? So square root of 2 over 2, which is right in your trig, right? Remember trig? Everyone, remember how your sine and cosine. Your cosine, it's a, what the book is using is it's using 1 over square root of 2. You always rationalize it with square root of 2 over 2, right? Everyone remember, and you don't, some of you don't. So you remember your trig functions on your unit circle. And 7 pi over 4 is right there, isn't it? This is 7 pi over 4. And then the cosine sine is what this point is, right? And at that point, it was always like the square root of 2 over 2 is your x value, and a negative square root of 2 over 2 is your y, right? Remember that? It's always, these pi over 4 places are always this way. This one is the square root of 2 over 2 for x, the square root of 2 over 2 for y. This one was what? A negative square root of 2 over 2, square root of 2 over 2, right? And this one was a negative square root of 2 over 2, and a negative square root of 2 over 2. And then this one was positive square root of 2 over 2, and a negative square root of 2 over 2. That was all those pi over 4 ones, right? Remember in trig? Yeah, you're plotting the points as you go around the unit circle. Well, rather than doing it this way, the book is going to do 1 over the square root of 2, 1 over the square root of 2. That is, it's an unrationalized number. Square root of 2 over 2 is a rationalized 1 over the square root of 2, correct? That's why in the book they're doing this 1 over the square root of 2. And then you're doing the cosine of 7. You're down here in this deal. You remember? Okay. So it's a cosine of 7 pi over 2. That's 1 over the square root of 2, which is an unrationalized number. And then the sine is going to be a negative 1 over the square root of 2, right? And then the minus the sine is a positive 1 over the square root of 2. And then the cosine is 1 over the square root of 2. So that's your A matrix for the transformation of a rotation of a negative pi over 4, which is a positive 7 pi over 4. That makes sense? And it's explaining it there in example 3 on page 73. All right. Now, I want to look at it 6. And this is the horizontal shear transformation that leaves E1 unchanged and maps E2 into E2 plus 3 E1. So if you think about the transformation E1, it's actually they're saying E1, right? So that is going to be 1, 0. And then the transformation of E2 is going to be E2 plus 3E1. So they're doing this. E2 is 0, 1 plus 3E1 is 1, 0. So this is 3, 1. So that's what that transformation is doing. And then your A matrix is actually the transformation E1, transformation E2. And that E1's transformation was this thing right up here, 1, 0. And E2's transformation is this over here. So that's your A transformation matrix. Okay, so that's what that problem 6 is telling you. Does that make sense? Okay. Now 8. It says the transformation from the R2 space to R2 first reflects points through the horizontal X1 axis, then reflects the points through line X2 equals X1. So it's saying that the E1 is translated through the X1. So it goes into E1, and then it translates it around the X2, X1, and that translates into E2. So we can figure out what. Let's see. If you look back on page 74, and it says that X1, it reflects it through the X1 axis. So if you look on the top of the page, when it goes through the X1 axis, E1, that E1 is actually going right back to itself, right? It's because after the translation, it's still 1, 0. That matrix is, right? You see what I'm talking about? That matrix there. So it still remains E1. Then when you go down and you translate it through the X equals 1 axis, that's that third one down, and you notice that it translates it from see, this goes from 1, 0 to 1, 0. And then when you go down, the third one down, it says it goes into 0, 1. Well, that's E2, right? Because the E's are all from the identity matrix. And so that's what they're telling it happens. Okay, and then what's it telling us? So then when we take our E2 and we do our first translation, and we go on up to that first one, it translates it into a negative E2, right? You see that first matrix it's saying goes negative. And then when you go down, if you go down to the one where it says y equals x, then it's translating that, and that's an E1. So it's translating it, and you get into a minus E1. So it's starting out with this identity E1. It's translating it into 0 minus 1. And then that's going back into a negative of E1. So it's a minus 1, 0. So if you do your translations, E1, translation E2, then really what this is, translation is E2, a negative E1. So 0, 1, and a negative 1, 0. And this is your A matrix, your translation matrix. Okay. Now, number 10, it's saying R to R2 first reflects points through the vertical x2 axis, then rotates it on pi over 2. So when it does the vertical, let's do the vertical. So that's that second one down. So E1 on that translation goes to a negative E1, and then E2 goes to E2. And then it says it rotates it rotates points pi over 2 radians. So at this point, what you have, this one is negative 1, 0, and then this one is 0, 1. So that's what you have. Then you're going to rotate that on pi over 2. So you're going to rotate this from here to here, and that rotation makes this E negative E1 talking about this thing right here, negative E1, then has to be rotated pi over 2, and that's going to be it's going to be if you look back at your 73, it's going to be a negative cosine of pi over 2, and then sine of pi over 2. And then that E2 is just going to be that second part, which is a minus sine of pi over 2 cosine of pi over 2. Well, your x, y values at this point on the unit circle are what? 0 and 1. So the cosine is going to be a negative, the 0, and the sign, pi over 2 is 1. And this one is a negative 1 and 0. So then your A has got to be 0, because this is actually a 0. 0, 1, minus 1, 0. So that's your transformation matrix. And notice that when you do 12, if you look at the rotation on page 74, that reflection through the origin, is the matrix minus 1, 0, 0, minus 1. If I did that right, that should be the same. It's backwards. It's 0, 1, minus 1, 0. It's not the same. And they're saying that it should be. And my contention is isn't. So. And let's say 16 says fill in the missing entries of the matrix assuming that the equation holds for all values of the variable. So they're saying, what does this matrix look like? Give you x1 plus x2 minus 2x1 plus x2 and x1. And then actually what it is, it's 0 times x2. Well, when you do this, it's just, this has to be, I think I wrote that, this first one wrong. That was a minus, isn't it? This would have to be 1 minus 1. Because when you multiply this times this, you should get that, right? So it's 1 times x1 should give you x1, and then minus 1 times x2 should give you x2. And then the next one should be what? Minus 2 and a 1. Because you multiply, see, you multiply the row times this, and that gives you that thing right there, right? And then you'd have to have 1 and 0. So your A matrix transformation is going to be 1, the first column is 1, minus 2, 1, and minus 1, 1, it's 0. So that's how you figure those kinds of problems out. 17 through 20, it says show that T is a linear transformation by finding a matrix that implements the mapping. Note that x1, x2 are not vectors but are entries in vectors. Okay. So so 18 is telling you wish that I hadn't gone that high. And it's x1 minus 1. So in essence, what they're doing for you is they're telling you this, that you have something here that you're multiplying by x1, x2. It's giving you, now that first one, this one right here, I would write it 3, negative 3x1 plus 2x2. Otherwise you get confused on writing it back. And this is x1 minus 4x2. And then it's 0, so it's 0, 0. And then it's 0x2. So once again, it's just figuring it backwards. So what we're going to have, this is when you're doing vector multiplication, this is a vector that is a 4-row by 1 column. So what you have to have, and this is a 2 by 1. So in order to get a 4 by 1, and to have this a 2 by 1, this has got to be a 4 by 2, right? Because in order to get a 4 by 1, you have to have a 4 by 2, a 2, these two, this 2 and this 2 have to match. And then it's telling you what it is, but this one and this one is telling you what this one is. So that when you're doing matrix multiplication, that's what has to happen. So that says that this thing has to be a minus 3 and 2. This has got to be 1 and minus 4. And this has got to be 0 and 0. And this has got to be a 0 and 1. That's why you want to be sure and write this thing this way, because if you're trying to go backwards and you write it 2x2 minus 3x1, you might flip them to that one. So this is the it gives you that matrix over there. Okay. Okay, I want to look at 22. It's saying the transformation of R2 and R3 be a linear transformation such that P of and what we want to find is find the x such that P of x equals -1, 4, and 9. So what we're doing, we got to find the A. And so this is x1 minus 2x2 minus x1 plus x2 and 3x1 minus 2x2. So this is going to, the A is going to be 1 minus 2 minus 1 and 3. And 3 and minus 2. So that's got to be our A matrix. Now what we want to do is we want to have this AX equal this B minus 1, 4, and 9. And we want to calculate that X. So what we have to do is we got to take this A matrix and augment it with this B right over here. So we're going to go 1 minus 1, 3, it's 2, 3, and minus 2, that's 1, 4, and 9. And then we'll do echelon, and then we'll get a value for x1 and x2. Will be what we transform into that. So then we just have to 1 minus 2 minus 1, 0. I'm going to multiply the first row by 1. So this is 1, and then 3. First row by minus 3, 0. That's plus 6, plus 4. That's 12, isn't it? Do that by a minus 4. And then that goes 0. And then I'm going to do this one and eliminate that one. So I got to multiply it by 2. 0 and 2, 6, 3, 0, 1, 3, 0, 0, 0. So then this says if I did it right, my x1, x2 should equal 3 and 3. Is that right? Seems like, did I do something wrong?
Yeah, I was about to say the second matrix, it's still supposed to be fluxed.
This one right here, and this is
The
which,
second matrix, first row. Because for that, you returned a -1 to a -3 when you did perform the actions in the first row. I'm sorry, third matrix there. The one right below the one you have marked.
the one that has the red
Yeah.
circles.
Yeah.
And so
Supposed
which,
to be you have, yeah, it's supposed to be -1.
This-
You have to put a -3.
this was.
Yep.
Okay. Okay. Then that makes this one -5, doesn't it? What does that make? +5? Okay, then it makes this one. So then, when we do that A transformation, that thing times those, it should give us, in other words, what we found. I can't remember that matrix. That matrix right there. 1 minus 1, 3. 1 minus 1, 3. The next column is what? -2, 3, and -2. Was that -2? I can't remember. -2, 3, and -2. If I multiply that by 5, 3, then it should give me that -1, 4, 9. Supposedly, if I've done it right.
Yep.
So that's what they're asking for. Okay. That's enough.